All right, guys, if you've got a 1994 to 2002 radio that says Theftlock up here and is showing LOC right here, and you found out that the phone number you used to call to get the code is out, this video is going to talk to you about how to get the code to unlock these without that GM phone number anymore. Stay tuned. All right, guys, it used to be when you got one of these Theftlock radios that GM used from Delco Electronics from 94 to around 2002, it's the one that says LOC. If it says LOCK or locked or anything else, this video doesn't apply to it. You want to look up in the right-hand corner, and I'll link up one of the other ones I've got that probably is more applicable. But if you've got one of these 90s ones and it says LOC, what you used to do is you used to hold the 2 and the 3 key down for several seconds. And it is, again, this only works on these radios that say Theftlock on them at the top of the screen area. And after you hold these 2 keys down for a certain amount of time, you would get a code, 3 digits. And then you'd hit the AM/FM button, and you get another 3 digits. And you used to call into a phone number at Delphi or Delco, and they would give you a 4-digit code to unlock the radio. Well, what these guys did is at the end of 2019, they got rid of this, right? So here we see a bulletin that GM put out in September of 2019, basically saying that this unlock procedure is temporarily not available. So they're saying, hey, you can't call this phone line because it's been turned off, and they're trying to find an alternative. So that's why the phones quit working. GM pulled the plug on the server that ran these things. And then a little while after that, GM put an update out. This one came out in November of 2019. And what they're saying here now is that they're still aware of this being turned off, and they're still seeking solutions. And when they figure out what they're going to do, they'll put a service bulletin out to replace this preliminary information. This is November of 2019. So after some more time came out, they eventually put out this service bulletin in December, I think. Yes, it was in December. And basically what they did in this big fancy service bulletin is they were clear, hey, all these Theftlock radios from 94 to 2002, all GM vehicles that used those ones that had this, what they basically, they went through what I just did, so how you pull the code out of it. But what they basically came out and said is the only way you're going to be able to do this, we got rid of the phone number. We got rid of the phone number, and so what you're going to have to do is you're going to have to send the radio off to an electronic service center. The dealer is going to have to send it off. So the dealer can't give you the code anymore. So if you go to the dealer, they're going to then send your radio off and charge you, or if it's a local thing, maybe they have an ability to just call or something of that nature. But the point is you can't do it yourself. You're stuck going to the dealer now. So what I decided to do when is put a video together is how are these codes stored in these radios, and how can we avoid spending that kind of money? These kind of radios are like $10 nowadays, maybe 15 at a salvage yard. Why on earth would I want to go to the dealer and pay any money for them to figure out this code? And plus you get these radios locked from time to time at the salvage yard. So what I'm going to do is show you how to do that. Now I'm going to show it to you in phases, so don't panic. First of all, there's going to be some math. There's no test though, so don't panic. I'm going to show you how to take this radio cover off on the bottom here and how to identify the chip that holds the code, but it's not an EEPROM. It's a processor, so it's a lot more involved. You don't have to do this to get the code, so don't bail out just because you see some soldering. I'm taking that out to get the information I needed to figure out on how to do it without having to take the radio apart. And in the next phase of the video after that, I'll show you how you actually end up being able to do this by basically simulating that you're a Tech 2 and figuring out how to talk to the radio over its communications bus. So this isn't going to be based on CAN, so there's nothing you can do with Bluetooth or any of that stuff. This is old school technology. This is not technology that uses CAN. It's not even class 2. It's a really, 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 really old bus. And we're going to walk through it together piece by piece. So let's get started. We're going to go through the first part, right? So here I got the radio that's a CD player. And I'm going to flip him over here. I guess I'm going to put him like this. And then just for comparison, I've got another one that's a cassette. I'm going to flip him over as well. And so we take a T15. You can see there's a little bit of a difference between these two, but the chassis are similar. There's going to be a heat sink here, and there's going to be in this case of the cassette, there's 2 T15s. that you have to take off to get this bottom cover off. And then on the CD version of this old radio, it should be pretty much the same. This one's a 95 and this one's a 98. There's one T15 here. As you can see the cutout where the same heatsink was used for the cassette models. Once the T15s are out, then there are some standard hex head bolts, and I'm using an English 3/16 to remove these. Got two here. And then on the other side, on the CD one rather, same size, but it's just the two here. So there's one here right next to the plug for the harness. And then there's another one over here. And then with these screws out of the way, we can take the top cover off. And then the same deal on the cassette version. You still have these two on the back in addition to the two we took off the top. So one by where the harness goes, and then one on the other side, all the same size bolt. And this should be it. Okay. Now this cover just lifts off, and we can see the circuit board inside, and we'll take the CD one off as well. On the CD one, it's kind of tucked under the front faceplate a little bit, and then it's got a little bit of a retainer here, so you just have to kind of pull it out sideways and it'll come off. So when we look at the boards, they're very similar. What we're interested in, though, this era of board that started in '92, there's no EEPROM holding this information. Instead, what we're interested in is this large chip here from Texas Instruments. This is just some kind of GM part number sticker that's stuck on there. But this same chip appears here, and it appears here. And there's different part numbers on these chips because what this is a microcontroller. Think of it like a CPU, like a central processing unit, but it's a specialized kind. Inside this big chip is a processing unit, RAM, which is working memory, ROM, which is read-only memory, and also an EEPROM capability, all in this one big device. The reason the part numbers are different between these two, so this one ends in 836 on the CD player, and then the one in the cassette ends in 833, and the reason they're different is they've got different ROM contents, so there's different programs on them for controlling these different entertainment devices. The other thing you'll notice is there's this kind of silicone type sealant around each of them, and you'll see that on a number of these chips, and 20 plus years it's kind of gotten kind of soft and sticky. GM put this on boards back in the day because they were worried about cold solder joints from vibration, and so they would put this around all these chips to hold it down. What I'm going to do is I'm going to go ahead and keep working on the CD one primarily. We're going to go ahead and cut all of this material off to get it away from the pins so that we can remove this chip. And we can remove this chip, put it into a reader, and we can read the code where it's stored in memory, which is the whole point of this. So what I would do for this is I'm just going to move these cables out of the way. And if they look like they're not going to stay out of the way as I'm cutting this off, I might just unplug them from here and here, but I think they can stay, and we can just hold them out of the way. But I'm just going to really get one of my X-Acto knives. I'm not going to film all this because not really anything exciting, and I'm just going to cut this stuff away and peel it off, and we'll come back when I've got that done. All right, guys, I started to cut this stuff away, and it's just coming off already from age, so I'll just go ahead and show it to you. Right, so it turns out, because of the age, it's not so bad. So I'm just going to go around and just literally peel it away from the chip itself. And then I'm just going to push it right off the board. You want to be careful when you're on the board side, getting it to dislodge so that it doesn't damage any components. Like under here, there was some sort of, looks like maybe a capacitor. And then we'll just kind of get it to let go right here. Definitely wash your hands afterwards, I would say. No telling what this material was. cooking in here for almost 30 years. But with this out of the way, then we'll be able to desolder the chip. And I'm not going to be using a hot air gun technique, although that certainly is something you could do for this. I'm just going to be using Chip Quick. I think it'll be the best solution for this particular situation. All right, so we've got this kind of insulating material off. You can see this is a PLCC type package. You can see the pins are right around here. And that looks like, just so we don't burn anything with the soldering iron, I think I will, after all, remove these two connectors. Just kind of get them started like that, so you don't put too much pressure on the wiring. Okay, and I can get those out of the way. I think this guy here, this ribbon cable, will be fine. We'll have room to get our soldering iron in there. Just going to try and get some of this stuff off around the top here because it's just going to heat up when we put the gun in there, or the iron in there rather. So might as well get it out of the way now. All right. Now the way Chip Quick works, if you haven't used it before, Chip Quick is just a way to remove a surface mount device like this. It's just some flux, and it's a special low temperature melting alloy. And the whole deal with this is it's going to contaminate, literally, the original solder and lower the overall melting point, and that's going to allow us to remove it without having to use a hot air gun or a lot of heat. So the first thing I'm going to do here, and hopefully there's enough light getting in here for you guys to see, I'm going to put some of this flux all around these pins, all the way around. This guy here, let's see if I can get him just to bend just a little bit out of our way. And you definitely don't want to go, you want to go liberal on this, I guess is what I wanted to say, because it'll make the process go that much faster. So I'm going to block your view for a second while I go do the piece in the back. Actually, get into the last little bit of this. I'll put a link in the description for this material if you're interested. All right, so now I'm going to come over here. Just going to move this whole deal closer to the iron. And all I'm going to do is I'm going to go find the end of this material. This alloy is very brittle, as you can see. So it's not like regular solder. So we're first going to get it on. So I'm just going to kind of run it around like this. Make sure that it's getting all these pins. And we're just going to do the same thing all the way around. This is another thing you don't want to worry about skimping on. Just put in what's needed to do this. I'm just going to be blowing periodically to get some of these fumes away from me. I'd normally use an extractor, but it's going to be too much noise, I think, for you on this particular video. And just get a little bit up on the top part here. All right, guys. Now, like I said, all you want to do is just go around the edges once you've got this Chip Quick on all these pins. And now we got this this fume extractor getting this stuff out of our face. You can get a lot closer here to see what we're doing. So I'm going to do these two sides, and there it goes. Right? It just almost started to lift. So I'm just going to redo this side. And this side here, and I think we're good to go. All right. So we got this guy off. What we'll do is we'll come in here with copper braid here. Just going to kind of scoop up the big pieces. And we can pull this guy back out and clean this up. So you can see it just kind of attaches right to itself. Kind of coagulates together. All right, let that dry up and we can clear that out in a bit. And so the next thing I'll do also is we'll take the chip itself. We'll clean up some of this. So we got a lot of this melted up material that was underneath, and that's probably why it took a little while to let go, because it was almost like a glue under there. We'll clean all that up and then I'll show you how you can read this. All right, guys, I've cleaned up the almost, I'm going to do a little bit more, get rid, some of the residual parts of that sealant out, but I did get, some of you watching this might have saw some pieces of the chip quick get over here, and I did remove that very carefully to make sure it did not pull off any of these small surface mount resistors or capacitors at the same time. Now what I'm going to do in here when I do a couple more runs with the wire braid over here is I'm going to end up putting a socket in here, so that I can put this chip back in here and end up doing some back and forth tests during what we're going to show today. Now the chip itself, if we take a look over here, so we've got this guy all cleaned up. Basically just ran the copper braid all along the edges to make sure that we didn't have any chip quick creating any shorts in any of the pins. All right, guys, I edited some of this out because you guys don't necessarily need to see me cleaning the chip up and installing the socket back in the radio. What I'm going to show now, though, is getting ready to read it. So these PLCC, plastic leaded chip carriers, they can come in different sizes, and this particular tool I have has one of the sockets to fit this 68-pin version. And they use these types of sockets. What you're looking for is a bevel on the chip, and you line it up with a bevel on the socket, and that tells you that you've got it oriented correctly. At that point, you just want to make sure that you got all these leads kind of like in the right spot so that it goes in evenly. You don't want to get it in there crooked, because if you get it in there crooked, there's a chance you might bend something. All right, so now we've got this guy set up, and what I'm going to be using tool-wise for this is a really old microcontroller, and there's not a lot of tools that can read it. It's not an EEPROM, right? It's a microcontroller. So this UPA-USB programmer is one, though, that has an adapter like this so we can read it. And the software only runs on Windows, so I'm going to be using this Windows laptop for a moment for this. And I've got this guy loaded up already, and I've set the device type as a TMS370 CX56, right? So that's the type of PLCC device that we're going to be reading. And so with that done, if I was to just come up here and say that I wanted to read the device, all right, there it is, read. If I say I just want to read this device, it's only going to by default read from like 0 to 1 FFF. And we actually want to read more than that, right? So that's not really going to give us the whole thing. It gives us something, but it doesn't give us the whole thing. And so what I really want to do is I want to see if I can read everything. So I'm here once I say that I want to read all of memory, right? 0 FFFF. And now I'm going to read the whole thing. This is going to take a lot longer. But now what we're going to do, I'm going to show you the data sheet in a minute here. Now what I'm going to do is, instead of just reading the RAM part, which is what it read by default, I'm also going to read the ROM part, which is also where the firmware itself resides, the EEPROM part. So after we get all this read in, we're going to save this, because all we really wanted to do is take a snapshot of what's on this microcontroller. And then we're going to put it back in the radio, and then we're going to go debug around to figure out where that code is. And I'm going to show you the methodology I used to figure this out as soon as this loads up, right? So this thing's chugging along, right? So obviously, late 80s technology here, right? So it was a barn burner in its time, but not anymore. All right, so now we've got this all read in, and now we have everything from address 0 to address FFFF, right? So if we cruise through here, we can see there's some random stuff here at the top. There's a bunch of blanks. There's a little bit of code here. And then we get back down to the RAM area, and we see there's some repeating sequences, and then we see the actual beginning of the firmware program itself that's been burned to the chip. And this continues for a while. And then we get down near the end, and there's some tables. You can see some fixed data. And then we've gotten past the core firmware, and now we're back to all zeros again. And I suspect when we get to the very bottom, we might see some closing data, or might not. No. All right, so that's it. So we've got an image of this guy, and then we can use this tool to save it. And what I'm going to do is I'm going to save this image, and then I'm going to pull up a different tool like a hex editor, and we can begin searching for information and trying to pick out of all of this what we're looking for. Now, I've obviously already saved several of these. I've saved several different radios. And the other thing I've done is I've saved images where I've changed to different user lock codes on the radio. So what you want to do is find out where in memory are those lock codes that you enter being stored. And then we'll also then from there be able to branch out and figure out where other things are being stored. So we got that. Now the next thing I want to show you is like on the data sheet itself, right? So this is the data sheet for this particular TI device, right? So we're looking at the PLCC packaging version, and we can see a little bit about this device, right? It has ROM, it has RAM, and it has an EEPROM. It's a very sophisticated device of its era. The EEPROM it has is one-time programmable, right? You can only program it once, and if you're doing like a firmware image for a radio and you just want to make one of these and churn out a few 100,000, that worked out great for Delco Electronics in the day. Now, what we're interested in understanding in the data sheet is the memory map, because that's going to help us read the image we just took, right? And so when we take a look at this memory map from 0 all the way to FFFF, which we just saved, we can see that we've got some information here about different RAM quantities that the different types of chips may have had. Some came with 256, some with 512, 1K, 1.5, 3.5, right? And then we can see also the EEPROM range and how much that would. And it varied by the type of chip, how much was stored. And then the same for the ROM. And this will help us, though, in our range of addresses with another piece of the data sheet that says, well, for this particular device, what did it have? What was its address range? And then we'll be able to map that back to the data file that we saved. So what I'm going to do now is I'm going to take a tool here, like to remove this, and I'm going to take our chip back out of this carrier, and then I'm going to mount it back in the radio. And then we're going to hook the radio up to some power. I've already kind of got this up here. I'll tell you about this in just a sec. Let me get all set up for this. And I'll show you how we're going to take some values from the radio that will now search for this file that we saved, taking a snapshot of what this chip has. All right, guys, we've got our microcontroller reinstalled into the socket that we put onto the circuit board of our Delco radio. And at this point, I'm going to power up the radio. And I'm going to show you a few things that we're going to use to then reference into the file that we saved, which was the contents of this microcontroller. So I've got just a bench power supply over here. I'll tell you a little bit about what this wiring is here in the back in a minute. Basically, what I'm going to be showing you here. I've got power coming from the connector on the back here, connected up to the 12-volt bench power supply. Same with the grounds. I've called out something that is very important for this exercise, which is a diagnostic bus. I've got a DLC connector so we can hook up a Tech2, and then we've got a little switch here that simulates us basically turning the ignition key into either the accessory or the run position, which we've just done. If we come back to the radio and we see down the top bottom here, it's upside down, of course, right, because we got the belly off. It's a locked radio, right? It's in the LOC mode. And of course, when it's in a locked mode, normally on these vintage radios, you'd hold the 2 and the 3 key in for several seconds, and at some point the firmware inside catches that and it says, well, that's 932, and if you press the AM/FM, that's 942. And we're going to write down those numbers, 932, 942. Now, you used to be able to go back, like I was saying earlier in the video, and put that number into a telephony system, and it would give you a 4-digit unlock code that would correspond to what you needed to do here. But I'm going to show you how we can get past that if we don't know it. Now, in this case, I know what the code is. I entered the code as 1234. And so we're actually going to go in here, and we're going to enter the code to show you that we do know the code to unlock it. I'm going to cruise up here to get to the 34 part. And again, it's upside down. Apologize for that, but that's the orientation for what we're doing, right? And so when we get 1, 2, 3, 4, we've got all that entered up there. It says secured. That means it takes the code. That's a valid code, so we're no longer locked. And if we were to turn the radio on, I don't have a speaker hooked up to this, but we've got the radio unlocked. We can scan channels and that sort of thing. So the reason we're interested in showing that code, that's the next thing I'm going to write down here, right? So we've got what GM calls the scramble code. And what we've got here is what GM calls the user code. And that's 1, 2, 3, 4. There's some other information, though, we're going to grab. And we're going to grab that using our Tech2 scan tool. And I'm going to bring that over into view here. Power on my Tech2. And there's a little bit of diagnostic capability that you can do with the radio from the Tech2. But for the purpose of what we're trying to do, to reverse engineer and figure out how this TheftLock works, this came out of a 1998, and I'm going to go into body because it's the radio, and this came out of an S10 SUV utility body. And we're just going to say that we had both the BCM and IPC because the thing I took it out of had that. All right, and so in the body menu, what I'm interested in this thing is this option called the Entertainment and Comfort Bus. These old radios are before the days of CAN, and they're before the days of Class 2. It's a really old proprietary bus protocol. And when we go in here, one of the things that's of interest to us is receiver identification. So when we press this, the Tech2 is going to go out over the connection we've done and talk to that microcontroller, and it's going to ask for 3 pieces of information: a software ID, the hardware ID, and the calibration ID. Now, the hardware ID is just the part number of the radio. If we think back to earlier in the video on the label on the radio, it's that number 0936055, right? That's the number that it's talking about there. And so we're going to write down these values now as part of what we're going to be interested in searching for. So we've got a hardware ID of 6055. We've got a software ID of 9396, and we've got a calibration ID of 0257, right? So we're just trying to kind of capture what the Tech2 was telling us, not necessarily in the same order, but because what you're going to find out is the only one of these that's really useful to us is the hardware ID. So at this point, for now, we're done with the Tech2. We can power it off. And we're actually done with the radio here for a moment, and we can power it off, and turn that off, and turn the bench power supply off. So one of the things that we'll want to understand before we can make use of this data is I need to teach you a little bit about how you look at numbers like this. So let's just take our hardware ID. So 6055. This is a decimal number, right? We call that base 10. What that means is that in this numeric system, the characters that represent the different symbols for this, there are 10 of them, 0 through 9. We can also represent this number in something called base 16. It's also referred to as hexadecimal. And we can represent this number in something called base 2, which is decimal. And what I'm going to do here in a moment is I'm going to show you what those values are, because those values are what we're not going to find this 6055 literally stored in the image from the microcontroller. We're instead going to be interested in hunting for numbers either in base 16 or base 2, and that's why it's important to understand those two. So let me get set up to show you how we take all of this information and go through the file that we stored from the microcontroller, and we find what we're looking for. All right, guys, we're all ready to do this next step now. Let me finish what I was explaining over here, right? So I was explaining about the different bases. Now we're going to show how this 6055 decimal number is represented in these other bases. So in the base 16, in the hexadecimal, it's represented as a 17A7. And in this base 2 binary representation, this one's going to be the most unusual if you don't work in the computer science or engineering field. It's a 101111010011. That whole string of ones and zeros is how the computer normally looks at and represents that type of number. I'm not teaching you this because of math. I'm teaching this so you can follow along with what I'm going to be doing in the video to show how we crack this code. Now, one more piece of data before we move on, right? These bases and how these numbers are represented. I think we're all familiar with decimal and base 10. What we have is each of these positions has a weighting, right? So this is the thousandth position, the hundredths, the tens, and the ones. And what that means then is I have 6 times 1,000 plus 0 times 100 plus 5 times 10 plus 5 times 1, and that gives me 6,055. That's the same thing here for base 2 binary, right? In this position, this is the ones position. This is worth 2. This is worth 4, 8, 16, 32, 64, 128, 256, 512, 1,024, 2,048, and 4,096. And if you were to add these numbers up, 4,096 plus 1,024 plus 512 plus 256 plus 128 plus 32 plus 4 plus 2 plus 1, you get 6055, right? So that's how you move between different numbering systems and have the same value represented. So now let's start applying what I'm trying to show you here and how we crack these kind of codes. So now we've got the file that we saved from the UPA-USB programmer, and we've just got it pulled up in HexD, which is a hex editor on Windows. And we're going to come in here and we're going to do some searching, right? So if I was to come in and try to search for the text string, the actual literal string of that hardware ID 6055, right? If I go and try to search for that, it's going to tell me it doesn't find anything, 6055. And that's because there's nothing in the literal decoded text of that value. So what I'm going to end up searching for, and what we're looking at here are hexadecimal values. So what we're going to end up searching for is strictly on the hex value side. So if I check that off, now even if I come over here and say, well, let me see if you've got a 6055, right? And I come over here and I don't have it, right? I don't have a 6055. And the reason I'm doing a space, right, we've got each number has a space and hexadecimal there, whereas we don't do the spaces if we're trying to search the text. So now what if I search for the hexadecimal representation of 6055? Okay, well, now I find it. I find it here. And actually, if I go through here and do it again, I'll find this number keeps repeating in several places. And in fact, I find out that this number repeats here, here, here. There's the other 17A7. And here. So it appears in these 4 places. And if I reference my data sheet and I look at the addresses, so these offsets I can correspond over to the addresses I'm looking at, I can see that I'm seeing these values like 1 Edward, like this particular value here. Let me just take this one. This one here is the beginning of our 17A7. This is 1 Fox 2 Alpha, 1 F2A. And I can see I'm sitting in my EEPROM area here. So now I know this is one of the things I'm looking for. And if I go through this, I'll find out that's only stored here. What's now super more interesting is, well, we had an unlock code. I'm going to go back to the top here. I had an unlock code of 1234. And it turns out that that's just stored literally as 1234. And there it is. There's the unlock code for the radio. So there's the code we had earlier for the hardware ID. Now here's our user unlock code. And if we go through and search again, what we'll find is this same repeating pattern through the memory contents. The microcontroller has made several copies of the same information here. There's 4 copies of the same information. I'll put these addresses in the video description. So now let's look for the money shot, guys. What's the master unlock code? So the master unlock code is, well, if I don't remember the code, every one of these radios has a master code that you would used to go in and take this scramble code, enter it on the telephone system that GM got rid of, and it would give you a master code. We don't know what the master code is yet, right? That's not something that we know where it is until now. So what we're going to do now is, well, we know it's a 932942. So let's go search for something like that. Let's go search for 0932. And we find, wow, right in our same space, right? So here's our hardware ID. And whoops, a touch screen. Got to watch out for that. There's our hardware ID. There's our user code. And here's our 0932. And right in front of it is 0942. Well, that's our code. And I've done this on several radios, guys. This is how it works. So they take the first number that you get when you press the 2 and the 3, and the second number you get when you press the AM/FM button, and they're just stored backwards. So what we're seeing here, instead of seeing the 932 first, we're seeing the 942 first. And there's a reason for that, because later on I'm going to get into some more detail about how to get this without pulling this chip out. We just pulled this chip, like I said at the beginning of the video, to figure all this out. I wouldn't recommend you go do all this work to do what I'm showing you. There's an easier way, and we'll get to that soon. This is the theory behind it. So there is stored backwards here, 932942, several times. And guess what? What I've found across going through like several of these, like a dozen or so of these radios, and then memory dumps that people have taken over the years and stored on some forums before they even knew stuff like this and compare this out. This is our master code right here. 1111. That's our master code for this particular radio. So there's not an algorithm with TheftLock. What happened, and I'll show you later how it's done over this bus connection, is in the manufacturing stage at Delco Electronics, these things were written to each of the radios. And they were not calculated by the firmware. They were just written to the firmware. And so we'll see this same thing written several times, right? So let's do a Missouri test here. Let's just scroll over without cutting. Let's turn our power back on, our bench power supply. Let's power back on our radio. It's going to come up locked again. But this time, we're not going to enter 1234, the user code. We're going to enter what the memory dump tells us is the master unlock code, which is 1111. And we still get a secure unlock. And we are in like Flynn. Okay? So that's how that works. Now, pulling this chip out and doing all this work, some people might want to do that. If you know how to do that, you're done. Maybe you don't even have to pull it. Maybe you can put a PLCC 68 test clip on this chip in the radio and read the information that way without having to desolder it. But I'm going to show you how you can get at this the way Delco Electronics programmed it. And we're going to read this out without even having to open the radio. So let me get set up to show you that and how we built up to that information. All right, guys, let me tell you a little bit about the setup I've got going here on this first stage of debugging, right? So I said earlier that we've got some wiring into the connections on the back of the radio, the universal connector that's used in all these series radios, and we've wired up a kind of a primitive circuit so that we can kind of look at the communication bus itself. So let me show you in the service manual what we've wired up here. So when you look at the back of this radio, there's kind of like two of these connectors kind of stacked together to form a unit, and they call that C1 and C2. There's a lot of speaker connections. What we were interested in, we said, we tied grounds together, right? So here's one of the grounds that we've tied together. Another thing that we needed to have here is we needed to have our power connections tied together. And another thing that we're interested in is on the other connector past all these speakers is this diagnostic signal, entertainment and comfort, right? So you remember that name from when we were using the Tech2. So this is the actual bus for the radio. And again, like I was saying earlier, this is ages before the development of the CAN bus that you see in cars today. And this is also not Class 2. This is something unique for the radios, and in some models, like maybe Buicks and Cadillacs, for some sophisticated air conditioning controls. This was a very proprietary GM-only thing. So that's the connections there, and then what we've done on the DLCC DLC connector rather, is we're interested in ground there, so we can power up the Tech2. So we've got our grounds there. We've also got our battery power connected, and then we're looking at the wire 14, which back in these days, 14 is used for other things today, but back in these days, it was used for this diagnostic signal for this entertainment and comfort bus. And so that's what we're going to be monitoring here, right? So in this Mac I've got, so I like to switch to I prefer my Mac usually. I only use the Windows stuff when I have to. I'm running CoolTerm here, which is a serial communications program. I've got a Keyspan RS-232 to USB adapter. And what I've got here is just a mock-up of a kind of circuit that you would use if you were reading another kind of radio, like a K-line type radio. And it's just to try and see if we can sniff that bus. We're actually not going to be able to get very far with this, but it's just to show you the evolution of figuring out what's going on here. So if I turn on the power supply for the radio, and then I turn actually I'm going to have you watch over here. So just turning the power on causes some activity. If we zoom in, we can see that we're getting activity recorded in the terminal. And then if I go in and turn the ignition key switch type thing on, we get some more activity. And then what we find out is just turning the radio on, we get more activity. We even get activity turning the radio off. And so what's happening here is on this bus, and I can't make this text any bigger, but maybe we can just kind of zoom in a little bit more. What's happening on this bus is every time the radio, comes up, I got power or I'm good, I'm changing a channel, I'm changing volume, what have you, it's putting that message out on this bus. And the reason for that is you might have vehicles, for example, that have steering wheel mounted controllers for changing the radio stations or changing the channel. And this is the kind of back and forth traffic that they would use. It's also the kind of traffic that would be used from the radio head unit to, say, a remote CD player or a remote cassette player, for that matter, right? So you see two values here, E0 and FF. And what's happening here is this particular circuit is designed to look at serial data like you would see on a PC or a Mac. And this protocol for this proprietary bus doesn't fit into that. And so what's happening is it's getting confused. And what we're actually seeing here on these hex values are the representations of zeros and ones, where the FF's a 1 and the E0, you can really treat it as a 0, because some of the bits are being perceived as 0 and 1 at the timing that this looks at. So next, I'm going to show you another level I went to debug this. I'm next going to hook up a small oscilloscope so we can see another view of this. So let me get that hooked up. All right, guys, what we've done is I've got one of these low-cost oscilloscopes. I use this periodically, and we've got this hooked up into the ground circuit of what we were looking at before, and we've got the probe for the oscilloscope tied into our entertainment and comfort bus over here. And then over here on CoolTerm, I've got it cleared out and waiting to capture something, right? So both the terminal program through our serial protocol circuit and the oscilloscope are all ready to look at something on that bus from the radio. And I'm going to just come over to the radio and I'm just going to turn the power button on. And if we take a look at the oscilloscope, over here, we'll watch that more than the screen. When we hit the button, we get a capture, right? And so now we've got a capture here, and we've also got a capture over here in CoolTerm. And so we've got the equivalent of like a 00111101, right? Keeps going like that. And so what we're looking at here is just the message that the radio puts out when it says, hey, I'm powering up or I'm powering down. And sorry about that, guys. I bumped the camera there. But if we take a look at what we're staring at here are the actual zeros and ones that are occurring here on the bus with these transitions from how long that the signal is held high and how long it's allowed to return to normal and how long it stays at the normal position before it gets changed again. So we're actually seeing our 0011101000, just like we saw over here in CoolTerm. So we got a good idea now that if we hook the Tech2 up and we do that same test we did before, we can actually capture and decode manually the commands the Tech2 is sending to the radio to read those memory locations. And that's going to be the next thing we do here to finally wrap this up in a way where you don't have to pull the chip out. But I just wanted to show you a little bit of the theory. If you're interested in a deeper dive on this kind of theory on the entertainment and comfort bus, there's a guy named Thomas Schmidt that really dove into this big time, and I'll put some links in the description for the work he did on analyzing this, particularly for the remote cassette players in these vehicles. So I'm going to get set up to show you the next and final step to actually seeing this code without pulling the chip. All right, guys. Last stage of this right here. So what I've done now is I've got an Arduino here, and I've got a shield that I've built from open hardware, and I'll show you a link down below. But it's something that somebody put together, like I mentioned earlier, for trying to debug a cassette player. But we're going to repurpose that and the sketch that's for this particular shield and use it for what we're trying to figure out, right? So we've got a couple of grounds going into this shield. We've got it hooked up to our entertainment and comfort bus, and we've got the power hooked up. And what we can do now is we got over here, it's actually, this is this guy I told you before that did this work on the cassette player. Definitely give a shout out to Stuart Schmidt here for the work he did out here on GitHub. And we're going to use this now to take a look at when we hit that radio power button, right? So the same test we did before, when we hit it this time, now we actually get the exact breakdown and decoding of what this is, right? So I won't break all this down for you because it's not super pertinent, but it is the same message that we were seeing in the other software and that we were seeing on the oscilloscope. So now we can actually kind of decode what we're doing. And what we're really interested in here is, if you look right over here for a sec, I've got the Tech2 and I've got it all set here to do that same receiver identification. And now if I look at the screen here, I'm going to capture what is the Tech2 doing, right? And so when I hit that identification, I am now going to capture all of that information and communication that gives us these three values, right? So now I know what are the messages that get sent to the radio in detail and its response. So for example here, this particular binary message here ends up being the message to the radio to start the sequence of asking it for what is the software ID. And then down here is this, and then give me the next location. And then this next one is give me the hardware ID, give me the next location, and then also for the calibration ID. So actually, if I go down here right now, and I go into this mode to send to the radio, and I give it that same command, say, hey, I'm a Tech2, and I want you to tell me what is your hardware ID. And the radio comes back, just like it did up here, and says, oh, well, here's the first piece of that information, the first two numbers. And I say, okay, well, give me, whoops, I need to give this, let me give the second two numbers. Now, see, I messed it up. Sorry about that, guys. Let me do it again because I accidentally hit the wrong key. So give me the first two, and now give me the next one, right? That's the sequence we're after here that replicates what we did up here. And now we get the radio coming back and telling us exactly, what the number is. Now, if we think back to what we did earlier, and I go back and I get that piece of paper that we were recording our information on, and we compare it to what we've got here, right? So we were saying that the 6055 is equal to this binary set of digits. And I mentioned here, when we look at it in the normal way, the most significant, the highest weighted value is on the left. And there's actually a difference here. We call that most significant bit is on the left. But this particular microcontroller actually uses something called least significant bit. In that case, everything's reversed. So this whole 1, 2, 4 from right to left actually becomes left to right. So now that number actually is represented as 111 0 0 1 0 1 1 1 1 0 1. So it's actually the same number we had before, just flipped backwards, right? So each bit is written in the other direction. And now it goes from 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 248, 40, 96. it's in that direction. And if we look at what we just got back from the radio, if we skip all this other information, again, if you're interested in the details of these messages, again, the description has some links, but it has to do with start bits and stop bits are these two on the end. Message priority are the next two. The message sender, so 101000 is the Tech2, for example, and a 101001 is the radio. And then there's a bunch of information that says, hey, this is what I'm going to give you. The actual message that comes back is this last position, and it actually gives it back to you in reverse order. And what we see is it gives me first so I asked for this first piece of information, and then I asked for the next piece of information. And so what I end up getting here is a 11010, and then you just fill in the other O's afterwards. It drops, they're not significant to it. And then I asked for the second piece of information, it gives me a 1100101, and that actually ends up being what we've got here. So if we reverse what we've got, it first gave us the second time it gave us the 11000101, right? If we just kind of draw a line here, and then the first piece of information it gave us was the 11101. Well, that's our 6055, right? So that is how we decode what we got back. And it turns out that this is not reading an address as much as giving me the hardware ID, but now we know where the hardware ID sits in relationship to the unlock code that we want. Right, so if we think about from the other computer I had out here earlier, and I'll pull that up in a second, we look at that dump that we had on Windows. We now know that where we sat in memory and where we need to get to is just a few commands away. And so what we can end up doing to decode this is we can just keep telling the radio, give me the next byte. Give me the next byte. Right? Give me the next byte. And I'll keep giving this command until I get to the master code. Right? So now I don't even have to unlock the radio. I don't have to open up the radio. I don't have to try to desolder this chip. I don't have to then go through this whole effort that I showed you guys. I'm actually just walking through that memory area. There's some empty values that we'll see when we go back and look at the dump. And then at some point, I'm going to get down to the value I'm looking for. So now I'm starting to get back into the value that I'm going to use as my measurement that I've got to the right place, which is now I've gotten to my 11, right? So I've gotten to my actual unlock code right here. That's what this was. And if I keep going, I'm going to now start getting into the value for the 942932 scramble code. So let me kind of bring that. I know this is kind of terse, so let me bring this back to you. I'm going to go take the dump we did before so that we can show a printout of that side by side, and I'll show you how this all matches. But guys, we just found the unlock code without having to do anything other than use a little simple free program in an Arduino. All right, guys, so let me kind of wrap this up and tie it together. So I've copied the memory dump over from the Windows laptop to the Mac, and I pulled it up in WX Hex Editor just so we can take a look at it. The addresses are going to be skewed up because I've squeezed it for space, but that's not what we're after here. We're just after trying to take a look and understand these values. And what we're trying to determine here, if I can figure out where I have my place in memory, and actually what I realized I did, I actually accidentally typed something there. So let's just move away from that. All right, so there's our 17A7. So if we remember again, if we think back to what we were showing, right, that's our 6055. So now we have a command to get this value, but more importantly, we have a command that puts us into a particular place in memory. So we have a command that puts us at reading 17A7. And then we also have another command that lets us read the next two values, if you will, the next two characters. So we get the 17, we get the A7, and then we keep walking down. And that's what we see in this screen capture that I showed over here. So so here's our 17A7, our 6055 in decimal captured. And then we just keep walking through here. And we get these next values, which represents our 01 and our 81. And then you see we have 1, 2, 3, 4, 5, 6, 7 zeros. And that's what we see here. So here, remember these, I said earlier, the way this tool works, the zeros and the ones are like parity bits, and then there's a space. So here there's no values. 1, 2, 3, 4, 5, 6, 7. Those are just 7 empty 0 values. And then right after that comes our master unlock code, 1111. And after that comes our 0942, 0932. In the case of this radio, that's the 6-digit scramble code, and that's exactly what we see here, right? So here's our 1111, comes back here again in least significant bit binary, and then we start seeing the beginning of the 0942. So the way to get this, if you go down, if you want to do this, replicate what I've done here, you can go in the description, you can go out to that GitHub, and you can build this particular shield, this particular Arduino shield here. I'll just take this guy apart here just for a moment so we can show what we're talking about here. So we take the Arduino off, right? And then we've got this shield here that you can build. Actually, I got a few of these spare boards from Oshkosh because there's actually a thing on Oshkosh to just generate this guy. Then you put some resistors in here. You leave the 22 one at the top empty because you have an actual radio where this guy's circuit was used for something else. So for the radio, you leave it empty, a couple of transistors, and that's it, right? It hooks up to the E&C bus, a couple of grounds, and power. Now, what you could do in developing something like this, and it's something I might explore doing myself here, what you could do, I think, longer term, is you could get something like this. It's like a OBD2 kind of case. If I can get this guy to open up for me. He's kind of stuck there. There he goes. All right, and so you can have a way to wire this up, right? And so one of the things I might look at doing here is redesigning this circuit board so that it fits in here and have like a little button to activate it and maybe a little panel to show the digits, and you could actually modify the code for the Arduino. You plug it into the vehicle, you hit the button, and it reads the code off to you. I mean, that's an idea of where some information like this could get applied into some kind of a tool or something like that. But anyway, I did this because, as I said at the beginning of the video, they got rid of the phone number that you could call. And I wanted to find a way to do this without having to pay somebody to do it or pay the dealer to do it, which is what they fell back on. And this turned out to be ultimately the solution that worked, right? Just some free open source sketch for your Arduino and a free shield for it that handles this problem. And then a little bit of the information like I've shown you here and reverse engineering what the Tech2 did and basically being able to type these commands in and then skip down to where this information is stored. I've tried this on several different radios at this point, right? So we showed the one here, which was the 6055. The other one that I've used that this works on is the 5855, which is the cassette player kind of version of this. And you're looking for radios that say Theftlock. So these particular radios, all exhibit the same design, and you can get the master code from there. So, hey, thumbs up for this, guys. This took a long time to figure out. I hope you found it interesting, and I hope it might help you if you have this problem. Certainly, if you don't, there's plenty of people out there that used to sell access to the phone number and recorded it, and it might cost you $20, and they'll give you the code. If you're not interested in doing all the kind of electronics work, that's certainly another option. If you found this useful, please think about subscribing. I publish these videos about once every week, and if you like this kind of content, that might be a way for you to find out about it sooner than that. Thanks for watching.